Well, if we really want to check how fast these different approaches are in practice, we need to time things and work with real data. We would like to generate array elements in a random order. We've already talked about how to generate our, well, not really, but pseudo-random numbers by creating a random object. We haven't talked about this before, but these are not really random. In fact, each element is deterministically arrived at from the previous one, but the way they do it is just highly invisible to the final user, and they look random. For the purposes of our testing, we're going to want to produce the same random sequence more than once. And we can use the fact that this is really deterministic. You can supply a new random with a parameter. The jargon is its seed, the seed of the random value generator. And then it will produce the same apparently random sequence over and over, starting from this same starting point. Very easy then to just fill the array. We go through the whole array, put an element in, and we just grab the next random result that we get from our random object R. Next, we need to consider the idea of timing. There is a stopwatch class. We can reset it so that it comes back to its basic state with an elapsed time of 0. Then we can start the stopwatch so it starts timing, and we can stop it. And then we want to read the result. We can look at the elapsed milliseconds, which is actually a property of the stopwatch object, like we had length for strings. And this allows us to get the total time that has elapsed between the start and stop, and in between we will put the thing that we want to time. Here we've got basic variables for our array size, this random seed. We create our new object, the stopwatch, calling it watch, and we want to keep track of the elapsed time, which we will make as a double. We will keep it in seconds. We're going to make it so this can run from the command line. We're going to use the args parameter in our main function. If it doesn't provide us with two values, then we will prompt the user to give us the array size and a value for a seed. But if we do have the two parameters, then they're given to us as strings, recall, in the args array, so we can parse them to be numbers. Similarly, for random seed, this will be the second element of the command line arguments, that is to say at index 1. We started from 0. We can test all sorts of sorting methods, and the pattern is going to be the same. Just illustrate one here. First of all, using the particular random seed chosen by the user, we can fill data with this specific pseudo-random sequence. Get ready to use our stopwatch with reset and then start it. And then here's one of our sorts. This will vary by the experiment. And when this is done sorting, we stop the watch and we can read back the elapsed time here in seconds by using the watch's property elapsed milliseconds and dividing by 1,000 to get second. And then we print out data saying what happened. This gets repeated over and over, but with different sorts. Here's some examples of runs in the notes. Let's actually try it. There are various ways to do this. One is to build it. I've changed into the directory where I have my source. I'm going to change into the examples. Sorting is the project. And remember, the executable is 2 directories down on bin debug. And here, let's just see what's there now. We've got our sorting.exe. So Let's now do mono sorting.exe. Oh, this time I will do it because I forgot to put command line parameters. I can say, let's do 1023 for the seed value. And it comes back very fast. Once you get down to just a single millisecond, it's not that likely to be accurate. I should probably try larger things, but already we can see that the selection sort and the bubble sort took longer. Let's try the same thing, except I will do it all from the command line. Remember, the first parameter was the size, and the second number was the random seed. Try a different seed, and we get similar results. It's not supposed to be exactly the same. Let's try something with more data. I'll go up to a length of 10,000, a different seed. And now that takes a little bit longer. All of them have macroscopic times. So the shell sort is doing better than the quick sort. And the insertion and selection sort, the bubble sort are then all longer. Let's go even longer. This will take a while. We're up to 100,000. Now that we're up this large, the quick sort is the fastest. The shell sort is a little slower, and the rest of these will be quite slow. I will jump to the end and not show you the whole time. So now look at the much longer times here, and this idea of order comes in. This last set has 10 times as many elements as the previous. If something is of order n squared, and you multiply n by 10, n squared is multiplied by 100, and it works out quite closely here. Selection sort was just under a half a second here, and 100 times that would be 49 seconds, and we're just under that. Similarly for the bubble sort, and roughly so for the insertion sort. 100 times 0.21 would be 21, or a little less, but roughly 100 times as much. The quick sort time went up much slower, from 6 milliseconds, or 6 thousandths of a second, to 16. Nothing like a 100-fold increase. The notes here have some other references for sorting. These are some sort of cool animations you can look at on the web here.